Yes, thank you for joining today's class. I completely understand that it's Diwali and you might have other commitments as well. But yes, we do not have a pre-Diwali uh, of lecture. So let us continue with our discussion. Um, at first, last class I had announced that this class will do some hands-on. But I guess you all have received the access to the virtual lab, right? You all have tried, anyone? I know Yuvraj did, but I don't think he's joined. So, anyone else tried anything with the virtual lab? Logged in or, ran some OpenMP codes? Anything?
Not yet,
Okay.
ma'am.
Huh? Okay, not yet. Okay, okay. Yeah, that's fine. But do check if you have access or not. And if you do not have, I guess you have because Yuvraj has used it, but I do not know about others. But do check. If not, please write to well. So the lab team, because when I checked yesterday, I do not have the lab access. So I've also written to them, and hopefully by next week I'll have it, and so that maybe if I get the access by next week, then we can do some CUDA hands-on on the virtual lab itself. So hence let us begin our discussion with about CUDA. You know, understand how CUDA works, what how a basic CUDA program looks like. Anyone here has worked with CUDA or any other programming modeling which involves GPUs? Anyone? Okay, so I guess uh, we all are starting with the CUDA programming model today. So we will start from the basics, learn the basics, and then move on to learn more important things about CUDA programming or more uh, critical things through which we can obtain the performance that you get through CUDA. So to begin the discussion, so far the programming models that we discussed were OpenMP, MPI, pthreads, right, and even Hadoop. But now we are talking about CUDA, which is a programming model meant for NVIDIA GPUs specifically. So why GPUs? Why you think we need GPUs? We were happy with the CPUs, and we have programming models which involve CPU computation. Then why now we need GPUs? Or what was the need or motivation to build GPUs? Anyone? It's okay. You whatever your answer is wrong or may be half correct. It's fine. Let us this is the introductory lecture, so we have to discuss. Otherwise, it's going to be quite monotonous. So please, whoever knows anything about GPUs, the silliest of things, please answer.
So, ma'am, basically to increase the number of workers.
Yes. You use the word workers. Is there any specific reason why you used it? Like, have you worked with OpenCL or you know the terminology of OpenCL?
No, basically, ma'am, see, the objective here is in the modern IT technology, we
Hmm.
need to parallelize parallelize things, right?
Hmm.
Uh,
Hmm.
so that is the basic funda. So to achieve that, is it not possible, right, to use CPUs to work process many things? So instead of CPUs, we are going with the multi-processing system, which can be achieved through GPUs by using GPUs. So that is the thing, like
Yes,
use case.
yes, you are right. You are right. So the terminology for this is the throughput that we achieve. That is number of instructions that we execute per cycle. Okay, or the the floating point. Basically, we compare the performance of systems in terms of how many floating point instructions are executed per second. So to improve the performance, to execute more floating point instructions per second and to increase this throughput, CPUs may not be good enough, right? Because CPUs have low throughput, although you may have any compute intensive task like a matrix multiplication, a vector addition, or any other program or application which involves a lot of computation. CPUs will not be able to give you a very good throughput. CPUs are slower when they are used for enhancing the images or any kind of graphics rendering. Okay, I'm glad that what you answered was not just an answer about ki GPUs are meant for graphic processing, but you are on the right path, as in you targeted the general purpose computation that we do using GPUs, that is parallel computing. Because you all might know that when the GPUs were introduced, that time no one thought about it like it will be used for any day-to-day task. It was meant for graphic processing, and hence the name also was like GPU, which is graphic processing unit, and they were built to be used for gaming or any kind of simulation or a special purpose kind of a hardware, right? But as the throughput that we could gain using CPUs started, saturating, and we couldn't get anything more beyond what was possible with the capability of the hardware using CPUs, people started thinking about how to then use some other hardware with which we can, or a hardware can assist our CPU to gain this better throughput. And that's where people started looking at GPUs to be a general purpose computing unit and not just a specialized unit for designing graphics or for simulating images. And the you know that's where the GPUs started being part of many different applications which are used now for any many day-to-day, you know web or standalone applications. The next question is, what is heterogeneous computing? Anyone?
So, ma'am, again, for the heterogeneous environment means we have get the facility to use all the like programming models. Uh, so we can
Mm,
get like we can use p threads also, like that is my understanding,
I
or we can
understand. I
use the
understand. Hmm.
so,
Uh, you are partially correct that we are talking about more than one type of unit, but it is not programming model, but it is the system that we use. That is, you combining different processor architectures in a single system, which can involve a CPU and a GPU, or a CPU and a FPGA, or a CPU and any other device, but two different architectures, processor architectures basically, in a single system. So this heterogeneity is in terms of different processing architectures. Is it clear? So this is what is known as heterogeneous computing. So this involves having a common code which will have separate functions which will execute on a CPU and separate functions which will be executed on a GPU. Is this clear? What heterogeneous computing is? It is not in terms of programming models, but it is in terms of hardware architectures. And this is a very commonly used nomenclature, heterogeneous computing. So when we talk about CUDA computation, CUDA is a heterogeneous computing programming model, and we'll see why it is so. The reason is CUDA program that cannot work only on GPUs. As in, a CUDA program that you've designed cannot does not execute only on the GPU. It needs the CPU to initiate the program, to do the necessary, maybe uh, declaring the variables or any other task of initializing the data, and only the specific part that needs CUDA computation is sent to the GPU. Okay, so we'll see an example and there we'll appreciate that. So yeah, so as I mentioned, we will have a CPU as well as a GPU. So what are the strengths of a CPU? What are the strengths of a GPU? And why we need both? So CPU was a general purpose processor with very powerful control logic, and hence CPU is optimized for any control intensive task where there is some sophisticated control logic. So hence CPUs can be used for any sequential, that is single threaded or complex branching task where you need to take these different control decisions. But if you want throughput, you have to move on for to GPU, because GPUs are meant for parallel processing and you have thousands of GPUs codes. It is very ideal for a high throughput task like matrix computation or graphics rendering. Okay, and the strength of a GPU is that it is optimized for any data parallel computation intensive task. It is suitable for workloads and simple control flow and massive data parallelism. So we need both, and they are designed and meant for specific things. So if what will happen if you choose to run something, some program which needs a lot of powerful control logic, GPU may not be able to support it well. There are a lot of branching tasks. The throughput that you get through GPU will not be good enough, and you might prefer doing those tasks only on your CPU. At the same time, high throughput tasks, if run on CPU, will not give you the throughput you expect. The throughput will be reduced because the number of cores are very less. But the high throughput task, if given to GPU with its thousands of code, it can it is ideal to run these high throughput tasks. So the third terminology, which is part of CUDA or GPU programming, is general purpose computing on GPUs, which is a GPGPU. And what is a GPGPU? As I told you, GPUs were meant for to be used as specific, task processors which were meant for graphics rendering. But as its popularity increased for doing any other task, the simplest tasks like searching, sorting, matrix operations, they were called general purpose GPU or GPGPU. So we we although we talk about start searching and sorting, it is not that the best searching or sorting algorithm, a sequential one, will do justice if we just move it to a GPU. Developers have to adopt these algorithms, or they have to redesign these algorithms such that they use some graphic specific concepts, and then they are made to be, efficient, and they're able to give the throughput. But this task is a bit cumbersome. It's not that straightforward. You have to rethink about what do you have at hand, and what are the resources that you have at your hand, and how do you design your program so that it uses all these resources and is able to produce the output in a very efficient manner. Hence, because of this, the programming models which were meant for CPUs were not good enough or could not be used with GPUs, and GPUs needed specific programming models which were meant to be used before with this hardware. And that's where CUDA and OpenCL were introduced, and they become widely used for this general purpose GPU programming. So the difference between the two, as we discussed, CPUs were single instruction, single data, and GPUs are single instruction, multiple data. And how they interact is CPU is the host. CPU is the one who is hosting the coprocessor GPU, and you communicate between the two, that is CPU and GPU, through its memory. So whatever you put, data that you put in your CPU is moved to GPU memory for processing. Once the data is moved to GPU processing, GPU takes the data, works on the data, performs the computation, and once the results are generated on your GPU, you move those results back to your CPU so that those can be used or displayed on the screen, or or can be utilized for some other task. So, any doubts so far with what we've discussed? Okay, so let us move on with our discussion. Now, how the how a CPU architecture looks like, we all have learned in the architecture. We've seen the von Neumann architecture. We know the basics of, we have a ALU, we have a control unit, we have a main memory, and that's then we communicate. We have registers, and that's how we communicate. Now, there is a huge difference between a CPU architecture and a GPU architecture. And a GPU programming model developer, a CUDA or OpenCL developer, it is for a CPU programming programmer, you may or may not know the architecture well. Means you may have some idea, but you can start programming without knowing the architecture in detail. But a GPU programmer, a CUDA programmer, OpenCL programmer must know the architecture of GPU, because if it does not know what different features it has, it will not be able to efficiently use those features and design the solution, the application which will be the most efficient, or will use the different architectural features which are available to you. And hence, understanding the GPU architecture is very crucial when it comes to CUDA program. So, to begin understanding this, let us first start with understanding that you have threads on your, a thread which we have seen in the CPU as well as GPU. We'll talk about its difference in the next slide, but a thread on a GPU is combined into a thread block, and this thread block forms a kernel grid, or a grid of blocks. And this grid of blocks, a thread will be executed on one of the cores on a GPU. Now, these codes are combined into a streaming processor, or SM. We'll see how SM looks. And this SM, multiple SMs form a GPU, and on which the different kernel grids executed on this GPU. What is the difference between a CPU thread and a GPU thread is CPU threads are still heavyweight. They are managed by the operating system. They are designed to minimize latency for one or through two threads at one time. But GPU threads are much more lightweight. You have thousands of them, and they are meant to maximize the throughput with a lot of multi-threading. That is, there are a lot of threads which are available, and that's how you hide the latency in your GPU program. So coming back to your streaming multiprocessor, is this image visible, or you want me to zoom it? Anyone? Let me zoom it if I'm not sure if it's visible or not. So someone is saying something. Is this better now?
Yes, ma'am.
Okay. So this is one SM of your GPU. Okay. As I mentioned in the previous slide, GPU consists of multiple SMs, which is streaming multiprocessor, and each SM contains different elements. Now, what are these different elements? Here, as you can see, there is L1 cache, which is shared amongst different SMs. Then there is L0 instruction cache, which is meant for each SM. Okay, because this is one SM. Now, there is a warp scheduler. Warp scheduler is the one who schedules or groups these threads into a set which is known as warp, which consists of 32 threads. Okay, and then there is a dispatch unit. This dispatch unit assigns this warp of 32 threads the instruction it needs to execute. Then there is a register file. This register file is shared amongst these many, you know, different units. Now, what are these different units? Int are the integer codes which perform integer operations. FP64 are the codes which are designed to execute or compute floating point 64-bit unit instructions. FP32 are the codes which are meant to execute 32-bit floating point instructions. You have load store units, LDST. These units are meant to fetch data from memory into for the into your register file, and then do the computation. Let the codes work on this data. Apart from that, you have a SFU, which is special function unit. A special function unit is meant to perform some specific mathematical operations like square root, cos, sine. These special function units are designed to do this computation much faster, and hence we have these. Then you have something called as tensor core. Anyone knows what the tensor core is? Because this is kind of talked about a lot recently when we talk about GPUs. Anyone have heard any news about what tensor cores are? Anything? which excited you about a GPU? Okay, so answer codes are codes which are designed meant for specifically matrix operations, as in they do not work on individual element, but they work on a size of matrix of 4 cross 4 or 8 cross 8 matrix directly. So these tensor codes are meant to do the computation for matrix, you know, operations of a size of 4 cross 4. So in one cycle, you will do computation of 4 cross 4 matrix, maybe multiplication, maybe addition, or whatever. So these are specifically designed for such tasks. Is the SM clear now? What the streaming multiprocessor is and what are its different components? Any doubts in any of the component? Okay. So, what do you think is the advantage of having a SM in GPU? Why do we need SMs? See, um, we assign blocks of threads to each SM. So each SM then independently works on these blocks of threads. So hence, in a way, it helps you to execute different codes simultaneously or different SMs. Other than that, these SMs share a type of memory in GPU, which is shared memory, and gives you, this helps you to execute some instructions which use shared memory very fast because this memory is local to an SM, and hence data access is very fast to this shared memory. Apart from this, a scalability is one of the very critical features because you can scale your SMs very easily or scale your GPU very easily with by adding the number of SMs. So if you can have one, you design an architecture for your GPU, and in that architecture there are different SMs. So the same architecture can be used for for a laptop. You can have, let's say, 4 SMs laptop GPU I meant. A server grade GPU can have maybe 20 SMs, okay, something like that, so that scaling also becomes easier if you have a SM. So if you found the SM picture a bit difficult, this is what a GPU, the whole GPU looks like with multiple SMs. So this is much more, interesting, and it has many more other features which we are yet to discuss. But this is how a GPU architecture looks like. V100 is one of their very popular GPUs, NVIDIA's. Anyone knows about like what are NVIDIA GPU architectures? Anyone can tell me what are those? Like what are names of NVIDIA GPU architectures? Or anyone knows what is the interesting fact about these names? Okay, so the fact is that NVIDIA GPU architectures are named after scientists. So there is Kepler, there is Volta, there is Pascal, there is Ampere, uh, there is current one is Blackwell. Before that, there was Ada Lovelace. So every 1.5 year, NVIDIA kind of introduces a new architecture, and the architecture name is after a well-known scientist. So you can check out these names and what are the different uh, updates that they do this to these architectures, and why they have to introduce it after every 1.5 year, why they are introducing a new architecture. So yeah, so this is how the tensor code looks like. So till Walt Pascal architecture, there were no tensor cores. So a computation which used to take this much amount of time in Pascal, at the same during the same time when tensor cores were introduced in the Volta architecture, you could do the same computation 12 times faster. You could do 12 times more computations compared to your Pascal architecture. So tensor cores really have helped in the matrix computation specifically. And where matrix computations are used? What are applications of this dense matrix operations? Anyone? Okay, we will talk about it in the next slides. I'll not give a hint right now. We'll talk about it next time. Okay. So coming back to different architectures. Now, as you can see here in this table, there is these. Here we are comparing four of the GPU architectures of NVIDIA. There is Tesla, uh, Tesla K40, which is a Kepler architecture. Then there is M40, which is a Maxwell architecture. A P100, which is Pascal architecture. P100 is a Volta architecture. Each one has different number of SMs, as you can see, 15, 24, 56. How we scaled with number of SMs as for newer and new architectures. Then the tensor processing codes. Uh, no, then there is FP32 codes, but 192 first, then 128, then 64 and 64. You will say that why you reduce the number of FP32 codes in the newer architectures. It's not that it is reduced, but what they did earlier in the earlier architectures, there was only one SM which was part of, you know, and multiple SMs were grouped together. But now they have all further divided this SM into four SMs. So each SM also has now four SMs, and hence that each SM will have 64. So this is actually 64 into 4 kind of scenario. So the number of cores are increasing with every new architecture. The tensor cores were not introduced till here. Pascal, Volta introduced them, and in the newer architectures, Ada Lovelace and others, we have more tensor cores as well. These are texture units which are meant for specifically to work with texture memory like cache or texture memory. Then the clock rate is obviously increasing. The the shared memory size per SM is also increasing. The L2 cache size is increasing with every new architecture. The register file size also has increased, which is number of registers which are available to your SM in SM. Then the TDP, so the power consumption, the number of transistors on your chip is increasing. As you can see, we currently have 21.1 because obviously the size of the transistors is also reducing. So hence we are able to fit in more and more. The GPU die size also has changed, and the manufacturing process is obviously different for every new architecture. So the difference between a CPU memory and a GPU memory is that CPU we had a CPU memory, we had an option of registers, we had an option of maybe different levels of cache, main memory, and a secondary storage, right? The GPU, it has for itself multiple types of memories, more number of types of memories or more types of memories than a CPU has. And two of the very important ones are shared memory and global memory. We will discuss the rest also in the later slides, but two very important ones are shared and global. Shared is a small, fast memory which is accessible by different streaming processors within a single SM. And global memory is the largest one, which is a bit slower. The latency is high, and it is shared amongst all the SMs. CPU memory is meant for host, and GPU memory is the one which we use in the device. So you need to explicitly, transfer this data between your host and device, and we'll see how it is done. Now, coming back to CUDA programming model, the the CUDA programming model uh, has a function which is called global. This global function is the one that executes on your GPU. We'll come come back to it. Before that, the execution model when it comes to a CPU and GPU is that if you have this CUDA code, this is a CUDA code. This is a .cu file. This .cu file, it will have only 5% of the code which is executed on the GPU, and rest everything gets executed on a CPU. And we'll see how that works. In terms of data, you move the data from your CPU memory to your GPU memory, do the computation on your GPU, and then once the computation is done, you have to move your memory back to your CPU, or the data back to your CPU, not memory, but data back to your CPU. So before we discuss about Coda, I also mentioned about OpenCL, right? So what we have seen so far is OpenMP. There is something known as OpenEC, which is similar to CUDA, which uses CUDA, but it's similar to OpenMP. Sorry, my bad. Uh, So if we have an option which is something similar to OpenMP and which is using CUDA, don't you think that's a good option to go for? Why we still have to learn CUDA? Because as we saw with uh, if we compared pthread and OpenMP made our life quite easy because it gave us direct options to not, and we didn't have to think about creating a thread, ending a thread. Um, we didn't have to bother about, you know, how they're scheduled. Nothing. We could just mention the number of threads, and those many number of threads could, just spawn using the pragmas, and OpenMP library took care of all the necessary details of this creation and deletion of threads and freeing the memory and all that. Then is that not a good option when it comes to GPU programming as well? Why we really have to think about using the CUDA? Anyone? So, okay, so the answers are there on the slides. Like with CUDA OpenCL, these are low-level programming models. You have you can fine-tune things. You can control the tiniest of the things that are happening in your code, and that offers you maximum flexibility in terms of how do you design it, the solution. OpenMP, OpenEC are great if you want to easily and very fast accelerate your applications. You don't have to do much, just use OpenEC and just use pragmas and just accelerate your code. But with CUDA and OpenCL, that's not the case. You can, but it allows you this fine tuning or fine grained access or a very low level access on how to work with your memory or how to work with your program. So in within between CUDA and OpenCL, why do you choose CUDA or why do you choose OpenCL? What is the reason why you should go for one of the two when it comes to GPU programming? You should be clear about why you are using one of the two. So CUDA is specifically designed and developed by NVIDIA for NVIDIA GPUs. You cannot use CUDA programming model with any other GPU. It has to be NVIDIA. They have put efforts, they have spent tremendous resources in ensuring that they have built a very good programming model which is capable of getting the best performance for their GPUs, which is very easy to set up. It has enough resources available in terms of uh, already provided solutions for different problems, have built have taken enough efforts to build different libraries with for CUDA, which can help you design solutions for many different problems. And there is lots that they have provided you so that you can efficiently design your solutions with for your NVIDIA GPUs. But what if a designer wants to create a solution and want it to be used irrespective of which GPU it is using? That is, if someone wants to design a solution which is portable, so this solution should be able to execute on a GPU as well as it should be able easily. It could be used on a FPGA. So in such a scenario, what do you use? That's where OpenCL comes into picture, which is a highly portable. It supports a wide range of processors, but it requires a bit more complex setup, and you may not get as much support in terms of programming, design and everything with OpenCL, but it is equally good. So, what are the applications of CUDA? These are some of the well-known applications which are meant and was this was designed with previously. So it could be any kind of computational simulations in terms of medical science, geoscience, finance, chemistry, marketing, modeling, biology, image processing. Apart from this, can anyone tell me what is the one other application which is where they're using the GPUs, currently at least, why Nvidia shares have shown, why they have made profit, why everyone is buying Nvidia GPUs. What is that application? Anyone?
Is it related to generative AI?
Yes, yes. So, yes, it is generative AI or basically machine learning, right? Could be generative AI or any other type of memory, machine learning application. But currently, the reason why we see so much popularity of GPU is because of generative AI. Because we are trying to train large models, which needs faster training with enough memory, enough GPUs, enough processing power, enough throughput, and that's what we are able to gain through CUDA or any other GPU. So let us take maybe 10 minutes break and let's come back around 9:25 so that we can continue our discussion on the CUDA programming model. So let us begin and continue our discussion on the CUDA programming model. So to start, let us talk about the Hello World program, the first CUDA program. As I told you, the CUDA program is saved as a .cu. The a CUDA program can be written in C or C++. So this CUDA program will uh, need a main function. This main function will be executing on your CPU. So when you
Ma'am,
say,
just
yeah,
one thing to for setup, is there anything we need to do? I mean, the special
for say
library or
the CUDA installation,
this program to run? I mean, actually run and test in our local machines.
unless you have a NVIDIA GPU, will not be able to do it on your local machine.
Okay. In my
So
laptop, I
if
can see NVIDIA GeForce RTX. I don't know whether
huh,
this
so
is the
then
one.
so yes, G4 RTX is your GPU, NVIDIA GPU.
Okay, okay, fine.
Hmm. So if you go to CUDA website, NVIDIA's CUDA website, you will find the instructions for installation. So there are two ways you can install. You can either download the whole library and install it, or you can download the installer and then it will get the necessary libraries as and when installing. So all the instructions are available to you on the website of CUDA.
Okay,
So I will also try to maybe add a link or so on how to go ahead with the installation. Or
okay, ma'am.
yeah, okay, yeah. So are you using operating system Windows or Linux?
My one is Windows. Windows.
Okay, it has support for both. That's not a problem. Yes. So I'll add the links and maybe a tutorial link in the same in the slides. So this CUDA program is it should be a .cu file, and yeah, hopefully also I'm hoping my means if anyone of you had checked what all notes are available to you, if there is a GPU not, I assume it is there. It must be there, but yeah, I have written a mail to. Well, I should get the clarification soon. So if we have the access to the NVIDIA GPU of the cloud, then everyone can try because not everyone may have NVIDIA GPU on their laptop. So better we get that access by next week. And I also request you all to check what access you have in your virtual lab. Yes, moving back to the programming model. So this code, hello CUDA, which is here. So this is executed on CPU. Now this line, as you can see, where you have these, this is a call to your GPU function, which is known as a kernel in your CUDA code. This is not same as your OS kernel, although the name suggests the same, but a kernel function in a CUDA program, in GPU programming, is a function that will be executed on the GPU. So only this function will get executed on your GPU. Now, once you run this line, the control will transfer to your GPU. You will start the computation on your GPU. Once that, how do you know that computation is complete? For that, it is must to use a CUDA's device synchronize, which ensures that whatever is executed before this line is complete, and only then you move on to the next line. Now, after this, the next printf statement will be executed on your CPU, which is welcome back to your CPU. Now, how this CUDA function is, the kernel function is defined, is you use this global so this keyword in your .cu file will tell you that this function is to be executed on the GPU. Okay, this is now you have a return type void, the name of the function hello, and the type of arguments it has received. In this case, it's void. What this is doing is just doing printf hello from GPU. It is telling what is the thread number and what is the block number. Now, what is thread number, block number, we will discuss. So, if you execute this code in or a hello code, it will. How do you execute it? The compiler that you use for CUDA compilation is NVCC, which is a CUDA compiler, NVCC, and you provide it the .cu file. You may provide a output file, or if you do not do that, it will create a .out. Very similar to our GCC works. This is NVCC, which is meant for CUDA. And then it will print hello from thread 0, thread 1, thread 2, thread 3, threads, so on. So that's a very simple hello world program from on a GPU. But how can you design a program which involves doing some computation on the GPU and fetching data from your CPU to your GPU memory and writing this memory back to your GPU? So this is how a typical CUDA program looks like. You will allocate some memory on your GPU. You will copy the data from your CPU to your GPU. Then we will call the kernel function, and then the kernel function will execute. Once the kernel function finishes its execution, the result that is calculated by your GPU has to be brought back to your CPU, and hence you need to again transfer data from GPU to CPU memory, and post that you release your GPU memory resources. So you can have more than one kernel. In that case, you will have a host core execution, then there will be GPU execution, then there will be host execution, there will be GPU execution. So I hope by now it is very clear to you all. When you write a CUDA program, it does not mean the whole program runs on a GPU. Some part of it will run on and execute on CPU, and some part of it or specific functions only will go to GPU for execution.
Ma'am, here more than one kernel that you mentioned. Is it like for CPU level processor one kernel and for GPU another kernel?
No. See, I specifically told do not get confused with OS kernel concept.
Okay.
Okay. Here, what it means is on CPU, you are running something with 4 threads. These are specifically CPU threads. Then there is a kernel function, CPU kernel function, which uses multiple threads of your GPU. Then you do CUDA device synchronize, you come back to your CPU, and you might, let's say, have another kernel function in your code, which will be called after this, that will again spawn multiple threads on GPU and it will execute.
Okay.
Okay. So there is no kernel concept of kernel in terms of CUDA programming for CPU. Kernel is only for GPU, and that too, the function that executes on your GPU is called kernel. Okay. So let us see an example of vector addition where there is only one GPU kernel. We will talk about multi-kernels later, but a single kernel, simple program, vector addition. So there are these 5 things that you need to do. First, allocate memory on your GPU. Copy this memory data from your CPU to your GPU. Then do the execution on your GPU and then move your data from your GPU back to your CPU. Then you can verify the results if you want, and you can free the GPU memory. So let us see each step how the code looks like. The first step is allocating memory on your GPU. So here you use a function which is CUDA malloc, and you allocate this on your GPU. Now why this is A? So we are doing a vector addition. Vector addition could be C is equal to vector A plus vector B, right? Then why is this D? Why do you need a D in front of A? Anyone, any guesses?
Is it denotes the array of integer or number?
Yeah, it's an array. It's a vector. Vector is an array, right, of numbers. Now, why it is there is a D in front of this is, as we talked about, CPU is a host, right? CPU is a host and GPU is the device. So, any when you are communicating between these two, it is better, and specifically the memory is going to be remain same, as in these variables are going to remain same for host and device. So if you use this nomenclature of adding a D in front of this A, you know that this array is device array. Okay, device array of A. So the one that will execute or will be given to your GPU will be D underscore A. The one that will use on your host for your CPU will be H underscore A. It's the same array, but because of this nomenclature, you can differentiate clearly and will not get confused between which is the device array and which is the host array. Is it clear? So here we are allocating 3 arrays. The first one is A, the second one is B, the third one is C, and we can use and check if there is an error in terms of memory allocation, and that's where we check if malloc has happened or not. If not, then there will be an error thrown that memory was not allocated because of so and so reason. Okay, so for vector addition, we need 3 arrays or 3 vectors, A, B, and C. A and B will be the input vectors, and C will be the output vector, right? And all 3 have to be allocated on GPU because we need data to be moved from your CPU to GPU and GPU to CPU back. So the allocation needs to be done. So that's the first step of your CUDA program. Allocate these 3 vectors on your GPU using CUDA malloc. Next is now copy the data from host to your GPU. So this is the host array that you have created on your CPU. This host array is initialized on your CPU, that is, you've given it some elements, and now you copy this host array into your device array by using the function CUDA memcopy. So this is the device array, this is host array, which is CPU array, device array is the GPU array, the size of elements, the number of elements in this array, and from where to where you are copying. So you are copying now in step 2, host to device. You are sending the data from your CPU to your GPU, for the computation. Similarly, you have to send the other array as well, which is
Well,
array B.
host array we have not declared in this example case, right? It is like,
Okay, this is yes, yes, yes.
okay,
It should
fine.
be the for yeah. What I'll do
Okay, I
is
got it.
maybe I'll upload the whole code as well. Hmm? Yeah, I'll
Okay.
create a sample code file in our existing this on Conta, and there I'll upload the whole code. You can go through the whole. Hmm? You have to declare. Yes, maybe I'll put it in the slides as well. To declare the host array, to declare and initiate the host array. Then you can copy it from your host to device. Then similarly, you have to do it for the second array, that is B array. Next, you execute the GPU kernel. I'll show that how it is declared in the later slides, but this is part of the .cu file, the main function. Hence, I'm discussing this first. So here you need to mention how many threads you want to execute your code with. Okay, CUDA has thousands of threads. You may not need always the thousands of threads. How many you need will depend on how many number of elements you are trying to do the computation. Okay, so let's say you are doing it for 1024 threads. Okay, sorry, 1024 is the number of elements. That is n is 1024 for in A and B. Both have 1024 elements. So you are saying that every block of threads should have 256 threads. Okay. Now, how many such blocks you need? It is number of elements, that is 1024 plus threads per block, which is 256 minus 1, okay, divided by threads per block. That is 1024 plus 256 is how much? One zero, sorry, 1280 minus 1 divided by 256. So how many threads per block we are expecting here?
Nearly 5.
Nearly 5, right? So, 5 into 5 thread blocks will be, but do you, I don't think we'll get, it will be 4, right? We are not sealing it. So,
Actually, it's 4.99.
yeah, so 4.99 should be like, I think it should be 4. The output here will be 4. We are not sealing it, so might, or, so basically for adding 1024 items, you need 1024 threads, right? Each thread should be adding one item at a time, or two items at a time. So we are now launching this code with blocks per grid are 4 and 1024 threads. Sorry, 256 blocks.
Ma'am, number of elements, what is it here? Is it array elements or?
So array elements.
Okay. Kind of a chunk of array element we are
Yeah.
giving to a particular block.
Yes. Yes.
Okay.
And then you wait for this kernel to finish its execution, and you do CUDA device synchronize. The third will be, okay, now we have finished execution. The result is computed on your GPU. And now we have to move this host, this device array to your host array by using CUDA memcopy and CUDA memcopy device to host. Okay. Step 4, 5 will include freeing your memory, maybe printing the C array, maybe verifying the output, whatever. It could be the step here. This is how the
What are
CUDA
the
kernel looks like.
ABCD, ma'am? What are these ABCD? DAB, DB.
So this is device AB. We allocated them here, na? Device arrays.
Okay.
The memory that you allocated on your GPU, you have to free it once you are done.
Okay.
You're freeing it here. Freeing the GPU memory that you allocated because you're done with computation, you got the output. This is the final step. This is the CUDA kernel where you calculate what is the index of each thread. So how each thread will know which index it should execute on is first step would be to compute the index of that thread so that only that thread will execute or work on those indexes. So this index we calculate using block dimension and thread dimension, and we'll discuss this in later slides in detail. So do not worry about it much now. But first part is to compute this index of thread. Then you do the addition of two elements A and BI into your CI using this index. You can verify if this index is less than number of elements so that you do not do computation beyond the number of elements. You can try out a similar example, which will be single precision AX plus Y, where the only change is you send a floating point, element A to this array, to this special function, create a CUDA kernel function and try to do this example. I will upload the vector addition example and then you can modify it, and try to run it as this single X, single precision X plus Y. So how do you manage the memory on GPU is use CUDA malloc function, memcopy function, memset function, and free function. So it will give an error. If it has completed without any issue, it will say CUDA success. Otherwise, it will return CUDA error memory allocation, and then you can check what is the exact error and fix things accordingly. The next is, let us talk about how do you get the thread index or block index, right? The one that we just discussed in the example. So how your threads how your threads are um, arranged on your GPU is something of in this fashion, where your you have three concepts as you can see here: thread, block, and grid. I have the concept of thread is clear. These are the GPU threads. Now, when from programmer's perspective, a programmer groups these threads into a block. Okay, a block of threads. Why this is important is when you group these threads into block of threads, each block is then assigned to an SM. Okay, one SM executes one block. Now, hence there is a limit on maximum number of threads which are allowed per block. Okay, which is 1024. And so your maximum block size could be 1024. Okay. Then when you hence you may have like thousands of threads, right? So thousands of threads, or sorry, maybe millions of threads that you want to put. And if the block size maximum is 1024, you need more than one block, right? So when you have more than one block, they are these different sets of blocks are what is called a grid. Okay. So as you can see in this figure, block has multiple threads inside it, and a grid has multiple blocks inside it. Okay. So block index or block IDX is gives you the block index within a grid, and thread IDX gives you a thread index within a block. So the block dimension tells you what is the dimension of the block. So how many threads are part of this block? And grid dimension tells you how many blocks are part of this grid. Is this clear? Is everyone on the same page here?
Yes, ma'am. Ma'am, I have one question here. Like the thread index, if someone given me one thread index in this framework, so is it universal that it will identify a particular thread? I mean, across all blocks, thread IDs are universal, or it should be accompanied with block ID always?
Yes, that's a very good question, and we will get to it in the next slide. So let's take this example. Here, number of elements is 6, and here the dimension of the block is 3. So each block has 3 threads. Okay, and grid here is number of elements plus block minus 1, which is 3 plus 6, 9 divided by 3. So 3 blocks of 3 threads each, right? We have here. Okay. Sorry, number of elements is, sorry, 2. It is 9 minus 1, 8. 8 by 2, which will give you 8 by 3, which will give you 2. So there are 2 blocks of 3 threads each. Okay. Now, if we try to print what is the grid dimension, now grid, block, and block are 3-dimensional, you know, are supported in your CUDA, which is it's a DIM3. So you can have 3-dimensional blocks and 3-dimensional grids. Okay, and when you need this is let's say if you're doing matrix computation, you might need a 2-dimensional block, a 2-dimensional grid. When you're trying to do uh, a, let's say, a image processing kind of a program. Let's say you're trying to calculate the intensity, the histogram, or apply some grayscale, and the each pixel has, let's say, different uh, 3 different values. So in that case, you might need a 3-dimensional data, so 3-dimensional grid. So now let us see what is the output of this. Okay, so you're printing what is the thread ID of what is the block ID, what is the block dimension, what is the grid dimension, what is the thread index, and each dimension for block and grid. This is part of this code. If it is not clear, you can spend 2 minutes to see what this code is about, and then we'll see the output.
This grade one, can you explain here? Within brackets, some expression is there.
Which line are you talking about?
Inside main program, third line, dimension 3 grid.
So you need what is the grid dimension, right? You know what is known as block dimension is block is number of threads which are part
Yes.
of each block, And
Yes.
grid is how many blocks of threads you have in your code.
Okay.
Okay. So how do you calculate how many blocks you have in your code? Is by using some formula. Or you could have replaced this with by giving only 2 here. Okay. But why you have used a formula to compute how many blocks you need is so that you can make this problem a solution generic. So later what you could do is you could just send an argument to your main program, the number of the number of threads per block. This could be sent as an argument, and if you do that, you don't have to, with this formula it will calculate automatically the grid size for every other configuration. So you do not have to every time manually change this value. Is it clear why we use a formula to calculate the grid? So later it could be that, okay, if this code is, let's say, okay, whatever, I'll call it a dot out. So a dot out, you could, if you had given, say, as input, if you give 6, so, and that is given as argument, it will be assigned to your block. So based on this block size, the grid size will change. Number of elements plus block size is 6, 6 plus 6. So it will be, say, only one block of 3, 6, sorry, block size remains the same. So in this case, yes, one block of 6 threads each will be executed. So we'll see the output here. If it's still not clear, we can go back. Okay. So here we are first printing what are the dimensions of grid and block here. Okay. Since we have assigned 3 here and there is no x and y and z, 3 is automatically assigned to the dot x of your block. Okay. Y and z become by default 1. Again, for grid, we have not assigned 3 dimensions. We have assigned only the first dimension. Hence, this becomes grid.x. And y and z become by default 1. Okay. So, in printing, you can see the grid.x is 2. The block.x is 3. The y and z dimension is 1 each. Okay. Is this clear? Anyone has any doubts here? Then we can discuss and then we'll move on to the next. Is this clear? So here the next print is happening inside the CUDA kernel function, which is here. What it is printing? What is the thread ID in the kernel function? What is the block ID? Okay, block dimension, the grid dimension. Thread ID is the 3 dimensions x, y, z. Block ID is the 3 dimensions for the block. Block dimension is the block. What is the dimension of the block? It is not specific to each block, but it is universal amongst, common amongst multiple blocks. The grid dimension also is common because the dimension is fixed, right? But each thread and each block might have a different block ID and thread ID. So you can see the output here. The first thread has the thread ID x000 in all 3 dimensions. Its block ID is 100. Block dimension is 311 because block dimension here remains fixed for all the threads because this is a fixed value. We are launching 2 blocks of 3 threads each. It's 6 threads. And these 6 threads, the first thread will have the thread. So these six threads are divided into 2 blocks. So the first block threads will have its thread IDX will remain 000 012, and its block IDX will be 111. Okay, its thread ID, the second block will have block IDX 000, and its thread IDX will be again 012. Is this, now, is this clear? The doubts are clear, or are there still any doubts? So this tells you that if you want the unique thread ID for your thread, you need to also use the block dimension to compute this unique thread ID. Because the thread IDX is unique within a block, okay? But if you want a unique ID for amongst all the threads of all the blocks, you have to use the block dimension along with thread ID to compute this unique number. Is it clear? Anyone has any doubts, or okay? So you all can spend some time, revisit the slides, and I'll upload the code for complete code for vector addition as well. Go through it, and then if you have any doubts, we can discuss in the next class as well. But general guideline when you decide this thread ID, thread block size, is that you decide the block size and calculate the grid dimension based on the application data and the block size. And how do you decide this block size? Is you consider what is the performance characteristics of the kernel and what are the limitations in terms you have in terms of GPU resources. So we will talk about how resources are important in GPUs in the later slides, maybe in the next class, because it will be too much information in one class. So coming back to similar example, as I was telling you, if you the same number of elements, but how the block and grid dimension changes if you change the block size. This is an example for that. Go through this and tell me if you have any doubts.
So this is the full program, ma'am, right?
Yes, yes, but there is no kernel launch here. This is just telling how you can change the dimension of grids along with block. So if the previous examples are not clear, this is another example where we are launching a kernel with 4 blocks of 8 threads each. Okay, so you have total number of threads are 32. Okay, and this is a one-dimensional. There is no two dimension, there is or three dimension. This is one dimension. So here, how the threads are assigned is each thread in one block will have its thread index starting from 0 to 7. Okay, another block, the block ID will change, but the thread index will remain same. The third block ID will change, thread index will remain same, and so on. So is it clear? This is a very simple example. Okay. So there are 3 types of functions. How do you calculate the unique index for each thread across in 2 dimension, 3 dimension? We will discuss in the next class. For now, you have clarity about what is a grid, what is a block, what is a thread, what are these indexes, how a CUDA program looks like, what is a kernel function, and what are different kind of functions we can write in a CUDA program. So there are basically 3 types of functions: global, device, and host. A global function is executed on device, that is on the GPU. So, and be very clear about that host means your CPU and device is your GPU. Okay, because your device is a co-processor and hence it is called a device, and it cannot be a host because it is not the main processor, it is the co-processor. Okay, so the global, if you just go through any CUDA program which is pre-written by someone, and if you want to find out what is the function that executes on a GPU, you can just look for this keyword global, and this is what is a GPU function which is executed on your GPU. You can call this from your CPU, you can call it inside any other function on your GPU, and the return type has to be a void. Okay, device is executed on the GPU, but it is callable from GPU only. A kernel, global kernel can call this device. A CPU cannot call this function. Then there are host functions. Now this host, you may or may not put a host on for a function. By default, if it is not put, also it will be a CPU function. But if you put it, it is good for your understanding, for better readability, easier to pinpoint, understand where this is executed. This becomes a host is what is executed on your CPU only. Okay, so you cannot call it from your device. This is callable by CPU only, and you may or may not put it. If even if you don't put it, it will be by default a CPU function. So if you want to time your code without without using any profiler of NVIDIA GPU, you can use this timing function of your CPU and put this timer before your kernel code and after your kernel code, which will give you what is the time for your GPU execution. This is one way you can time your CUDA kernel. Otherwise, you can use your default profiler, whichever tool you are using, and we'll learn about the GPU profiler in the next class as well. So I think for now, let us I think stop here. I think you all better process whatever you learned so far, and then maybe you move on to what is the CUDA execution model. Okay. So if there are any doubts, you can tell me now. Ask me now, or we will meet next week.
I have one question outside of this. I mean, we have the quiz, second quiz, right? So what are the,
Yeah.
sessions will be included for that quiz? Is it from starting first session till date or?
No, I think quiz 2 I have included questions from OpenMP and I think MPI.
Okay.
Yeah. So it is whatever was covered after the first quiz. Even the third quiz will be based on whatever was covered after the quiz. I've
Not
used a
getting.
few.
Can
I
you
think
come
I
on? Yeah.
yeah. So I think it has MPI, OpenMP, and one or two questions on Hadoop. That's it.
Okay.
And the third quiz will be based on CUDA and whatever I cover after this. But mostly CUDA only. I think. Third quiz will be on CUDA. Any other doubt? Okay, then I think we can stop now. Happy Diwali. Let us meet next week and continue our discussion on CUDA and learn more about what is the execution model of CUDA, whether the way what the way the programmer designs the code is the same way the execution happens on GPU. Let us learn more about it. Then we learn more about what are the criteria we need to consider when we talk about gaining performance with a CUDA code. Is that straightforward approach or it's a trial approach? We will also talk about how profiling helps you to design better applications, CUDA applications. What are the different optimization techniques you can use with CUDA? So it is going to be a quite interesting few sessions next few with CUDA. And in the meantime, I request all of you to check your virtual labs if it is set up or not, what kind of machines you have in this virtual lab, if you have access to your GPU or not. And if not, do write to the lab team, get it fixed. Unless you try things, you will not be able to enjoy and learn how they work. So, and now that the labs are set up, we should make best use of it. And I've also put up the instructions in the announcement to ensure that if you are using a lab, please do not forget to switch it off. You have to turn off the node because it's on cloud. It's a limited resource, so better turn
Okay,
it off
ma'am.
on time.
Ma'am, Taxila, I mean, yeah, OSA, there is a lab platform, and this quantum is a different one.
No, this is a virtual lab. At least I have received an instruction where it says that on Takshila, uh, maybe I'll just show you the manual that I have received.
OSA, there is some platform spin up we spin up, right? And now this quantum I have not used as
So,
well.
ma'am, thing is that you always used to use the term quantum. So, Taxila and quantum both are same, right?
Oh, yeah, Conta. Sorry, I use Conta.
Quanta,
I'm,
yes.
I'm, I'm sorry. Yes, see, on campus we have we call it Conta. My bad. It is basically Takshila, Conta, are
OSA, okay, here
Moodle
OSA.
platform, Moodle platforms. So you can see here. Can you see my screen now?
Yes, ma'am.
So here, eLearn portal. If you go through here, it allows you to click on the My Virtual Lab button. Is it visible? Can anyone try going to eLearn? elearn.bits-pilani.ac.in.
And can you ping this URL if you have, and we'll try.
Oh, okay. I've typed it in the chat. But for me, if it shows my no labs available. What it shows you all? Can you see your lab there?
Yeah, so hi ma'am, like I can log in through OSHA. So there I
Hmm.
can log in through the web console. So it open
Okay,
like
so
a
here,
VDI system.
okay.
So do I
In
need to
here it
install something? Like
Ma'am, I have this URL I pinged. Is earlier we used to have this. Now is it different? Change?
so this is the so I sent you. This is the link that I've. So if you because I can't see those labs, I do not know exactly where it is asking to access. So maybe I'll upload this on Conta. You can go through this and see if this works. If you follow this and see if this works. Okay. And I'll once my this is once my access is available, then I'll upload what I tried.
Okay.
Okay. I'll upload this. Okay.
yeah, so ma'am, my question is that do we need to install something in the
So
virtual lab?
now that's the problem. I have not tried it, so I cannot tell you what is installed and what is not installed currently. So once I have access, I'll upload whatever announcement in the announcement what needs to be done. So I've written to the
Um,
team. Once I receive the response and I know how to go ahead, I will let you know. I'll put it up on announcement.
Okay, ma'am. Yeah, next time if you can walk us through at
Yes,
least, it'll helpful us. Yeah,
yes.
fine, ma'am.
Yeah. Okay. Sure. Thank you.
Thanks. Thanks.
Thank you.